Hello, welcome to the second video on aldehydes and ketones. We'll just finish off bits and pieces here. All right. Now, there's one thing I forgot to mention for the last one. The reagents for the triiodomethane test. The reagents are iodine, as you can see, and sodium hydroxide. Aqueous. You just add them together. Add these two things together, and if it contains this group, as we saw in the last video, you'll get a yellow precipitate of triiodomethane, that stuff. And the other thing, plus the corresponding carboxylic acid. Now, interestingly, they've shown the corresponding carboxylic acid as that, which is RCO. That. Now, the reason they've shown it in the salt form, if you remember, if we used ethanoic acid, you would actually get sodium ethanoate, okay, because you get the carboxylic acid forming, but then that would react with the alkali you're using. So you'd actually end up with this iron, which it says in the syllabus, okay, and the sodium source of it. All right, that's why it's this. All right, so there you go. Now let's try and do the mechanism, this thing here. Okay, now let's move this up. Let me show you something really nice. Okay, I'm going to have to bring something in from somewhere else. I think it's cover 2. Oh, that's not the right one. Let me get rid of that. I think it might be cover 1 then. All right, this one. There you go. This is beautiful. This is an electron density. Shows an electron density around a carbonyl group. Okay, so a carbonyl group, as you all know, is a C double bond O group like that. Okay, and there it is. And these are electron densities. Now, don't forget, there's 2 lone pairs on the oxygen here. Okay, and these just show the overlap of the electrons. But if you look here, this is a bit of a nice picture showing that the carbonyl group, the oxygen of the carbonyl group, is electron rich because oxygen is electronegative. It will pull electron density towards it, and the carbon here of the carbonyl group will be electron poor, so that will be positive. So what we're going to look at now is a nucleophilic reaction that's going to add to here. Okay. Now, I hope that makes sense. So we're going to show the last mechanism that we do on this course. All right, which is nucleophilic addition. This is the fourth and final mechanism. But unfortunately, probably it's the most complicated as well. Okay, which is just life, isn't it? But there you go. Okay, so first of all, let's have a look at another addition reaction. If we've got a double bond, okay, and we react a double bond with something like bromine, BR. As you know, I'm not going to go about the mechanism, but the BR adds across the double bond. Okay, and we end up with 1,2-dibromoethane. Now, this is, what do we call this guy? Well, this is an electron-rich source. Electron-rich. And this guy attacks this. So this is known as an electrophile. Okay, and this mechanism is therefore known as electrophilic addition. This is an electrophilic addition reaction. Okay. Now, what we're going to do is a similar thing, and now we're going to have a C double bond O. Now, interestingly, or not, as you're whatever you think, all right, this has a dipole. This one doesn't have a dipole. This one doesn't have a dipole. It just has a double bond, which are electron rich. But this one has quite a big dipole. So what's going to attack the carbon here is a nucleophile. All right, nucleophiles don't have to be negative, but they can be. But they must have a lone pair. So Nu shows a nucleophile. All right, and then something's going to attack this side. So in this one, we're going to get the carbon is going to add on to a nucleophile like this, and the oxygen is going to maybe add on to a hydrogen, as we're going to see. So the original thing that's attacking is a nucleophile. Nucleophile. And this, if you add across a CO, this is going to be nucleophilic addition. Okay, it's not electrophilic addition, it's nucleophilic addition. But the same thing is you get one product. Okay. Now, there's quite a lot to talk about in this nucleophilic addition. All right, so we better get going. All right. What we're going to do is we're going to add. I wish I could use different colours here. All right, we're going to add. Oh, it's a bit scratchy. We're going to add HCN across the CO. Okay. And what are we going to get? Well, eventually we're going to get this. We're going to get C. We did my original colours. Blue, blue. And then there's the O. Now, let me do this in red just to show you what I mean. One side of it's going to get a CN added to it. The other side is going to get an H added. So we're adding an H on one side of a double bond and a CN on the other. Okay? And it's going to add across the double bonds, and we're going to get this weird thing, okay, which we're going to talk about in a minute. Okay, so what are my reagents? Reagents. Well, it's obviously going to be a carbonyl group because that's what we're adding across. We're at this group here, plus HCN. Okay. Now, annoyingly, well, not annoyingly, HCN is a weak acid. It will split up to H plus and CN minus. And let's have a quick look at the CN minus ion. It's a triple bond there, like that. It has a lone pair on the C and a lone pair on the N, and it has a negative charge, and it's called a cyanide. This is a cyanide ion, okay? And HCN is obviously hydrogen cyanide. Very nasty stuff. You don't want to mess around with that. If you want to look up a James Bond film or something, it's called prussic acid because they use this a lot in James Bond because it kills very quickly. All right. Anyway, so we've got cyanide, and that's what we want. But unfortunately, because HCN is a weak acid, we don't get many of these, okay, because it's weak. So we get few cyanide ions. So we have to do a little trick, all right? And what we do is we use sodium cyanide. Now, sodium cyanide is an ionic salt, and that will totally ionize, providing my CN minus ions. So the CN minus ions originally are being provided by sodium cyanide, okay, there, purely because this guy is too weak to provide many of them. So as you'll see, we add a little bit of this. We don't have to add much, a bit. We add a bit of this, and it acts like a catalyst, okay, because it provides CN minus ions for the start of the reaction. All right, now all that said and done, let's go on with the mechanism, because otherwise the video will be too long. All right, so as I said, as you can see in the syllabus, we're going to react HCN and an aldehyde. I'm going to use an aldehyde to start with. All right, so let's have a look at my aldehyde. I'm going to use a very simple aldehyde. I'm going to use ethanal. There's ethanal. Okay, and I'm going to use NaCN. I'm going to use HCN. All right, and I'm going to use heat. Always get a bit of heat going. All right, so what happens first? Now, this obviously gives me CN minus ions. This does, but it doesn't give enough to do anything. Okay, so this is a reversible reaction, and this top one is going one way. So the CN minus ion, let's try and do it in a different color, comes along here. Okay, here's my CN. All right, and it's got a lone pair, which you must draw on the carbon, and it has a negative charge. I keep picking the same color here, and it has a negative charge. Okay, there we go. Now, what have we got to show? We've got to show our partial charges. So this is delta plus, and this is delta minus. And the first thing that happens, nice white for this one, the electrons from here attack here, like a proper nucleophile, like always. Nucleophile. Attacks this. At the same time, these guys from the bond go onto there. So what does that give me? This gives me this thing. CH3. There. C. There's the H. Now there's the O. But the O now has electrons. It has two lone pairs on it now. And it has a negative charge because the electrons have run off and jumped on the oxygen here. The CN at the other side, though, there, has formed a proper bond now, like this. Okay, so that's that. That's the first bit of the reaction. Okay, and you've got to learn this, I'm afraid. All right. Now, so the CN attacks the C of the double bond, the delta plus, and you get this thing in the middle. Now, floating around at the top here, we have an HCN molecule. All right, and these aren't very good at ionizing, but this is delta minus and this is delta plus. So what happens is one of these electrons from the oxygen captures this hydrogen, and these electrons go onto the CN. So what do we get now? We get C, CH3, OH. Let me do that in a different color because that's a new H. We get the CN here. And what goes down the bottom? My original H. And look at this, what happens up here. This CN, we get plus, CN minus with this lone pair, because that's what this forms. Now, we started off with CN minus, and we end up with CN minus. So the CN is regenerated. And that is very typical of a catalyst. Oh, how do you spell catalyst? Yeah, that looks good enough. All right, that's catalytic behavior. So the CN is regenerated. So you might think, well, it's not the same CN that went in. Well, it doesn't have to be. A CN is a CN. All right. So even though we only use a little bit of this to give us our original CN minus ions, once it gets going, it gets going. Because now I've got this, and it will form that of the next reaction. So once it gets going, it will get going. All right, and we end up with this weird thing here. All right, what is this thing? Right, let's draw it out nice. Let's draw it straight. Okay, there's 3 C's in a row. Off of this one, which one is it? Off of number 2, isn't it? There's an OH there. And let's try and name this thing. Okay, right. Oh, looks horrible, doesn't it? But let's go. Right, it is 3 carbons in a row, so it is propane. It's got the CN at the end, so it's propane nitrile. Now there's this weird thing. There's an OH on my propane nitrile, and it's on number 2. So this is called 2-hydroxy propane nitro, and it is an example of a cyanohydrin. These are called cyanohydrins. This is the cyano group. This is the hydrogen group. All right. Don't worry too much about that, but it's a cyanohydrin. Now, interestingly about these cyanohydrins, as you can see, or you might not be able to see, is that this guy here, okay, have a look at this carbon. It has 4 different groups around it. So there's one group. Let's try and change colors for these. There's the second group. Third group will be this one. And the fourth group, let's say this one. Okay, so this reaction often produces chiral compounds. Okay, as you can see. All right. Now, this is a bit confusing, and we don't really have to go into this too much. We can talk about this in person, I think. Now, the CN, the original attacking CN, attacks. Let me move this up a bit, everything up a bit. It attacks this thing, this CO bit. Now let's start where we started. This is a CH3. Now this thing is, well, let me try a different color. This thing, this whole thing, let me do it nicer than that. It's not very good, is that? Right. There we are. This is CH3. This thing is sp2 hybridized. So this whole thing is planar. It's planar. Now my CN doesn't attack from the side like it looks up above, but it attacks from the top of the plane. There's my lone pair, minus. Or it can attack from the bottom of the plane. All right, there's my same thing attacking from the bottom. So if it attacks from the top, we get this kind of thing. What's this? OH dot CH3 and CN. And if it attacks from the bottom of the plane, we get CnH, CH3, OH. So that's why if it attacks from the top, you get one isomer, one optical isomer. And if it attacks from the bottom, you get the second. Let's call this the first optical isomer. Let's call this the second optical isomer. Okay, so you'll get a mixture of both optical isomers, or both, I don't know if you remember this term, but these are known as enantiomers. You get both enantiomers. What ratio will you get them in? Well, it's just as likely to attack from the top as the bottom, so you actually get a 50-50 mixture of optical isomers. Okay, there you go. So that's that. Now, that's the mechanism, and this mechanism, by the way, the first act was nucleophilic. Okay, and as you can see, it's actually an addition reaction. So this is a nucleophilic addition reaction. Okay, and as you can see, or if you look at the syllabus, nucleophilic addition on our syllabus, it's the reaction between HCN and either an aldehyde or a ketone, but it's a carbonyl compound. Now, very quickly, just to finish the video off, I'll do exactly the same thing, but this time I'll do, instead of the HCN attacking an aldehyde, I'll show it attacking a ketone. So the only difference is there's a methyl on the bottom there. All right, so let's do this. The CN with its lone pair, you got to remember that, and its negative charge attacks this carbon. Why does it attack this carbon? Because it's delta plus, delta minus. At the same time, these electrons go there. We get the intermediate, CH3, O minus, Cn, and also the bottom, CH3. Yeah, all right. Now, what's special about this guy? Well, it's got lone pairs there and there. There's a passing HCN, which is itself delta plus, delta minus. These attack that. These jump on there. And what do I get? I get this CH3, CH3, OH. I get this thing. All right. Now, what's this thing called? It's not exactly the same as the other thing, but let's have a look. Let's draw this gently around the longest chain. There you go. So it's going to be, again, it's going to be called propane nitrile. Now, what's on my propane nitrile? There's a hydroxy. There's a hydroxy group, and there's also a methyl group. Now, what comes first alphabetically? Hydroxy does, because H comes before M, and they're both on number 2, so this is known as 2-hydroxy, 2-methyl propane nitrile. And it is another example of a cyanohydrin. Okay. All right, that's enough for now. Let me go and post this, and we'll talk about this more in class. All right, bye-bye.